はい。で、please start. So,
So, good afternoon, everyone. Let's start the afternoon session. The first speaker is Shintaro Yanagida from Nagoya, and the title of his talk is Shoe Algebra of Superconformal Vertex Algebras. So please start.
Thank you for the introduction. And as an organizer, I would like to thank all the speakers and all the participants. And so, in my talk, I want to explain you the so-called. I will pronounce it. This person by zoo. And so, zoo algebra. Yeah, zoo algebra is about X algebras. And also, I want to give you some new results which were obtained by the joint work with Sato Ryo-san of Aichi Institute of Technology, so very near to Nagoya University. And the preprint is posted on archive 2 weeks ago, I think. So anyway, my talk is about vertex algebras. So I would like to begin with a recollection of what is vertex algebras. So this one already appeared in Iwanes-san's talk and Nishinaka-san's talk yesterday. But anyway, so vertex algebra is some linear space V equipped with infinite family of binary operations labeled by integers j. And I will call it by j's product. And some distinguished element vacuum. And so there are several axioms that mainly, so they say some constraint on this infinite family of J's operators. And to explain that, it is convenient to consider the generating series of J's products. And here, so this notation appeared in Nishinaka-san's talk yesterday, but I want to explain it again. So this is a binary object, binary operation. So given two elements A and B of B, we have some new elements AJB in B. So fixing A and varying B, we have a linear operator AJ on B. So for each integer J, we have a linear operator AJ on. And so this series is a formal series in terms of variable Z, and the coefficient AJs in the space of endomorphisms. And there are several axioms, but important one is the locality, the so-called locality. And this is a definition of vertex algebras. But so it's a little bit obscured. The meaning of this locality axiom is obscure. But we can restate this locality axioms in terms of this series AJ or vertex operators in terms of these two families of relations. The first one is the so-called skew symmetry axiom, and the second one is the so-called Jacobi identity. And so the skew symmetry and the Jacobi identity appears in the axiom of the usual real algebras, and these are, how to say, some analog of the real algebra axioms. Also, in terms of J's product, these two relations can be rewritten in this way. The second, the first one is nothing but a skew symmetry, and the second one is also called Boucher's identity. So anyway, this is what is vertex algebras. And I want to also introduce a so-called I want to explain the additional structure of vertex algebras, the so-called conformal or Biasolo element. So as the word says, so this structure explains some structure, something like Biasolo algebras. The definition is as follows. So an element L is called the conformal element of set of set C if defining Ln by the n plus 1 product of V, Ln, L, then Lm and Ln satisfy the Virasoro relations. And this relation can be rewritten compactly in terms of the so-called lambda bracket defined in this way. And the Virasoro algebra relation can be rewritten this way. And what should I say? So here is the first standard example of vertex algebras, the so-called affine vertex algebras. So this one also appeared in Shinaka-san's talk, but anyway, so given a simple real algebra K and level small k of complex numbers, so we have a module, the so-called vacuum module VKJ of the affine algebra K hat associated with a simple algebra K. And this module VKJ has a unique vertex algebra structure in this way. And it also has a conformal structure, the so-called Sugawara vector. So this one is actually satisfies the Virasoro relations. And this VKJ satisfies some additional conditions, and this type here, VKJ. And in the end, the module VKJ is a so-called vertex operator algebra. So it is a vertex algebra equipped with Virasoro element and satisfies some additional conditions. So anyway, this is a standard example of vertex algebras. What should I say? So anyways, a vertex algebra looks like a very complicated object. And in order to study them, we use some nice invariants. And about 30 years ago, Yonshan Zhu introduced two invariants, the so-called C2-person algebra and Zhu algebra. On the first one, I explained something in two years ago, this workshop. And I will not explain this C2-person algebra, but I will focus on the second object, the Zhu algebra. So this is an associative algebra defined for vertex operator algebra. So in this V, vertex algebra has a Virasoro element, conformal element. Given a conformal element L, then the operator L0 is semi-simple. So we can decompose V in terms of the L0 eigenspace decomposition. Using this decomposition, we introduce a quotient space of V, quotiented by some subspace V star 2. And this one is a linear span of A star 2B. And the star 2 is defined in this formula. So here, by delta A, I denoted the L0 eigenvalue of A. So anyway, so using the conformal structure, we can introduce some new operations. And using the second operation, star 2, we define the subspace B star B, and we take the quotient. This is the underlying linear space of the Zhu algebra. And this AV is an associative algebra in terms of this product. The product star is defined, induced by the star 1 operation defined in this formula. And the statement is that this is associative. So anyway, we given a vertex operator algebra V, we have some new associative algebra A. And this AV is a very important object because AV describes the representation theory of this vertex operator algebra V. The theorem says that the simple module over the given VOAV corresponds bijectively to the simple modules of this non-commutative algebras. So classifying the representation classification problem of representation theory of Barrett's operator algebra B is reduced to the, how to say, ordinary classification problem of the non-commutative algebra A. And how should I say? So this is an example of the algebra for the fine Barrett's algebra I used before. So VK denotes the Barrett's algebra. And we have some Sugawara element, Virasoro element. So we can, then we have some associative algebra. The result is that this non-commutative algebra is isomorphic to the universal enveloping algebra of the simple B algebra K. So K was a some simple B algebra. And then given the algebra, we have the universal enveloping algebra UK, and this is some non-commutative algebra. The result is that the algebra is isomorphic to UK. And one more remark is that the Sugawara element or Virasoro element and the class of this Sugawara element. So this, I denoted by this bracket the class of the element L in the algebra A, in the quotient space A. The statement is that this element is belongs to the center of the non-commutative algebra. So this element commutes with any other elements in A. The next example is a little bit complicated one, but this is a so-called W algebras. The W algebras is a class of Barrett's algebras, and this is defined by the quantum Hamiltonian reduction or quantum duality reduction of the affine Barrett's algebra. And for this reduction, we need the data F. The F is some important element of the given simple real algebra K. And given such F, and we can construct some complex. And taking the zeroth cohomologic space, this H0 has some Barrett's algebra structures, and this is nothing but the W algebra. And what should I say? So what is the zoo algebra of this W algebra? The result is that if K is not the critical level, H check denotes the standard notation of a dual Coxeter number. So anyway, for almost all level K, the zoo algebra is isomorphic to the so-called finite W algebra. So it is also obtained by some reduction of the universal enveloping algebra UV. So the situation is a little bit complicated. So let me explain the most simplest but non-trivial case. So let us take K to be the SL2, and let us take F to the nilpotent element to be in this lower triangular one. And then the resulting W algebra is isomorphic to the Virasoro algebra. And the level K is related to the central charge C by this formula. So let us recall the definition of the Virasoro Barrett's algebra. So let us consider the Virasoro Lie algebra. Then we have the Barman modulo of Virasoro Lie algebra. Then some quotient in this way. And this quotient has a Barrett's algebra structure, and this is nothing but the Virasoro Barrett's algebra. And in this case, the zoo algebra turns out to be just a polynomial algebra of one variable. The variable x corresponds to the class of the Virasoro element. defined to be in this way. So anyways, so L is an element of module, and the class of this element L is a generator of the polynomial algebra, which is arithmetic Zoo algebra of Biasrobotics algebra. So anyway, so these are the standard theory of Zoo algebras. But yeah, so anyway, the Zoo algebra A is very important one, but unfortunately, this object is very difficult to study. So determining the structure of algebra structure of A is very difficult in general. And also the definition of A requires B to be VOA or some to have some Hamiltonian, so-called Hamiltonian LZ. So we should use the eigenspace decomposition in terms of LZ of B. So that's the original theory of Zoo algebra is a little bit restricted one. But about 20 years ago, Ishii Huang introduced a generalization A tilde with complex parameter gamma. Some generalization of the original one. And this theory is applicable for any vertex algebra, not necessarily to be VOA. The definition is as follows. This is type of B. A tilde is also the quotient, also a quotient of B, but taking quotient is a little bit different one. So we consider a subspace spanned by dot two product, and then this dot product is defined by this formula. And the statement is that this quotient space has associative algebra structure in terms of this operation. The operation dot, the product dot is induced by the dot one product. The dot one is given by this formula. So this formula says that taking some residue, and here, so A and B are given elements of B, and A is just a vertex operator of A acted on B. But here we insert some very funny function. But Huang shows that if B is a VOA, so there's some Virasoro element, so that the original A can be defined. The Huang shows that this new algebra A tilde is isomorphic to the original. So this statement says that Huang's theory is a true generalization of the original theory of the algebra. And so anyway, so A tilde has some parameter gamma, but from now on, I want to focus on the case gamma equal 1 and neglect the symbol. So anyway, this is a comparison of the original one and the different, the new one, tilde one. So comparing these two formulas, the new definition looks a little bit more complicated than the original. But I want to explain in this talk that this new definition, generalized one, A tilde, has several advantages. The first point is that determining A tilde is simpler, easier than the original way. The second one is that it has some nice geometric meaning, and using that, we can introduce the so-called Suji analog of the theory of Zoo algebras. So let me explain this first point, and I want to explain several new computation determination of the Zoo algebras. And So that, and here I want to consider the so-called superconformal vertex algebras. So this is a vertex algebra. This is a family of vertex algebras equipped with some nice structures, the so-called superconformal structures. So there are several vertex algebras here. And n equals 0 case is nothing but the Virasoro vertex algebras. I have already explained. So this is generalized by the Virasoro, right? And the structure is encoded in terms of the lambda bracket in this way. But anyway, for one case, this is the so-called Nebel-Schwartz vertex superalgebra. So it has an even generator L as Virasoro element. Additionally, the one odd element G. So this one is a super case. So the linear space D becomes super space. And so L is just the Virasoro one, but G satisfies this condition, and this is nothing but the primary condition on G. And G itself satisfies this lambda bracket. And of course, the element L generates the Virasoro vertex algebra as a sub-vertex algebra inside P n equal 1. The second n equal 2 case, this one already appeared in Shanhan-san's talk in the first day. So n equal to superconformal algebra. So this one is generated by two even elements L and J, and two odd elements G plus and G minus. And L is Virasoro. J is some primary of conformality 1, and G plus minus is primary of conformality 3 over 2. And the other non-zero lambda brackets are given in this way. And this symbol suggests we have a n equal 1 subalgebra generated by L and G plus and G minus. So anyway, increasing n, we have a bigger and bigger vertex algebra. And the most biggest one in this line is the sort of n equal 4. This is superconformal algebra. So this has L and J0, J plus and J minus, 4 even generators, and G plus minus G bar plus minus, 4 odd generators. L is Virasoro, J is current, and G plus minus is a looks like n equal 2 or 1 case, and there are several more complicated lambda bracket structures. And of course, the n equal 4 contains n equal 2 as a subalgebra generated by these elements. And I will show later that there are other two superconformal algebras, the so-called n equals 3 case and big n equal 4 case. Big n equal 4 is different from n equal 4, more bigger one exists. But I will mention them later. So anyway, we have these little bit complicated, but in some, but these was some complicated vertex algebras. But we can determine the algebra structure of these vertex algebras. So here is a definition of H. And we have 3 lemmas to compute or determine the structure of H. First, the generators of vertex algebra induces the generators of H through algebra. The second one is that the Virasoro element induces a central element of H. The third one is the most important one, and this one holds only for the new or generalized definition of H, and not hold on the original definition of the algebra. The statement is that we can neglect translated part, and the first statement is that. The second statement is that this one is the left hand side is nothing but the supercommutator in H tilde. So recall that H tilde is super algebra because B is super. So anyway, the statement is that the supercommutator in the zoo algebra can be calculated or can be read off to be the zeroth product of the original vertex algebra. In other words, we can neglect higher lambda that because recalling the definition of lambda bracket. So zeroth product corresponds to lambda 0. So constant term in this series. And so this relation says that the lambda first and lambda second, the higher lambda terms doesn't appear in the relation of H. So for example, in the complicated case, the n equal 4 super conformal algebra. So let us look this relation. So in order to obtain such a relation, we should check the original lambda bracket in the vertex algebra. So let us here. This is a lambda bracket between J plus and J minus. And we can neglect lambda. We can be on. It is enough to take the constant term in terms of lambda expansion. So the relation between classes J minus and J plus. The supercommutator is given by J0. Yeah, we can neglect. This term. Yeah, some of rules says that. And we obtain this relation. Another example is which one? Yeah, let us check in this relation, G plus and G minus. In the vertex algebra level, that's a little bit complicated structure, but we can neglect D term and higher lambda term. So the right hand side can be neglected on the level of zoo algebra. So in the zoo algebra, on the zoo algebra level, the classes of G and G bar supercomplex. So anyway, so by simple observation, we have these commutation relations in ordering the zoo algebra H. And carefully looking these relations, we find that these relations are nothing but the relations in the enveloping algebra of some least algebra. So at this point, we can expect that this zoo algebra H must be isomorphic to the universal enveloping algebra of some least algebra. And after some calculation, we find the following consequence. The zoo algebra of n equal 4 superconformal algebra is isomorphic to the universal enveloping algebra of the following least algebra. So this one is defined here. PSL22 is some least algebra, and this index, this symbol denotes the centralizer in this least algebra with respect to some element F. F minimum is an element of PSL2, and it is a so-called minimal nilpotent element. And explicitly, PSL2, yeah, this is a projective limit of SL2. And F minimum is given by this supermatrix. So here, this is a standard notation of supermatrix. And F minimum is given by, F minimum has only non-trivial entry in this block. And this block is given by the large F. These E and F and H are the standard SL2 triple. So our theorem says that we have an explicit isomorphism of superalgebras. These are the generators of the algebras. These generators are given by this lemma. So the generators are induced by the generators of the original or given vertex algebras. And the corresponding generators of the enveloping algebra is given by these elements, and explicitly they are given in this way. A similar result holds for n equal, but the 0 is a bit trivial, but n equal 1, n equal 2. Anyway, these algebras can be rewritten in terms of some universal enveloping algebra. And the appearing these superalgebras has a similar form. And these results are compatible with the so-called reduction and commutes with taking two algebras phenomena. This means that the vertex algebra and superconformal algebras are nothing but affine W superalgebras. So these vertex algebras can be obtained by some quantum Hamiltonian reduction. So then, this n equal 0, 1 to 4 superconformal algebras are kind of W, and examples of W superalgebras. And the appearing real algebra data is common to the data appearing in the algebra description. So here is a little bit complicated structures, complicated examples. But as I said before, the n equals 3 superconformal algebras, and the algebra, we computed the algebra of Bn equals 3. The result is a little bit different from equal 1, 2, and 4 cases. So we have enveloping algebra part, but also we have the Clifford algebra. Yeah, Clifford algebra appeared in scope by Professor Wang. And here is n equal 4 case. The vertex algebra itself is very complicated. But we can compute the algebra H. The result is similar to n equals 3 case. We have enveloping algebra part and Clifford algebra part. So anyway, these are the results. And then in the remaining 5 or 6 minutes, I want to explain what is the algebras for supersymmetric vertex algebras. So the formulation of supersymmetric vertex algebra, we need the super variable formulation. So by capital Z, I denote the pair of the even variable small z and odd variable, or Grassmannian variable zeta. And the axiom of Suji vertex algebra is very similar to the ordinary one, but we replace the field by superfield and translation by odd translation. Just one comment is that in this odd translation, there are mixing of even and odd elements. So this is the essence of supersymmetry. So please remind that the Suji structure on vertex algebra is essentially given by these out translations. Other actions are almost the same with non-Suji version. So anyways, this is a kind of analog or extension of vertex algebra. So we may expect a similar theory of the algebras. And before talking that, here is an example. So NY equal 1 super conformal algebra, a Nebel-Schwarz vertex algebra, has some structure of NK equal 1 Suji structure. And so in the Suji case, the lambda bracket is replaced by the capital lambda bracket. So we have in the operations, so we have infinite family of operations, but in the Suji case, we have two labels. The first one is the same with the ordinary case, but the second one is a subset of capital J, the subset of the index 1 through n. When using this capital lambda bracket, the NK equal 1 Suji structure can be expressed by just one line. So the superfield formulation compactifies the complicated vertex algebra structure. And here is our definition of two algebras for Suji vertex algebras. So given Suji vertex algebras, we consider this operation, dot operation. But here, because we are considering supersymmetric situation, in the original formula of dot product, we used residue and Durham differential. We replaced them by super residue and Berezinian differential. The statement is that considering this quotient space, we have an associative product induced by the dot one product. Unfortunately, as an algebra, as a super algebra, this H delta V doesn't see any single Suji structures. So given Suji vertex algebra, we can define an ordinary non-Suji vertex algebra. How to say underlying non-Suji vertex algebra. This one is non-Suji one. So we can consider the H the non-Suji algebra. And as an algebra, the Suji algebra and the non-Suji algebras are isomorphic. But in this our Suji algebra, there is some differentials induced by the out translations. So this one encodes some Suji structure of the given Suji vertex algebra. So here's the example. So n equal 1 case. So we have one generator G and capital lambda bracket like this. As I mentioned before, the Suji algebra H D is isomorphic to some enveloping algebra, but this enveloping algebra has new content, the differential induced by the other translation. So differential means that this is a linear operator, but is nilpotent. So this relation encodes the Suji structure of this Suji vertex algebra. And we have similar results, higher n case. So time is almost up, so let me summarize. So we determined the Fuan's formulation of two algebra for superconformal vertex algebras. The determination is much more simpler than the original. And we also proposed Suji's algebras, and it is natural in some sense. And the study is just the beginning, and there are many open problems not yet solved. For example, the representation theory level, yes, I think as far as I understand, n equal 1 to 4 case, the representation theory is almost done. But the complicated n equals 3 or n equal 4, big n equal 4 cases remain. And also, we may expect some relation to the talk of Kano sensei in the past day. So he mentions the quantum toroidal shape one. And not this algebra itself, but the Yangian limit of this algebra may be related to the Suji-Barks algebras. And studying them, our Suji's algebras may play some role. Anyway, the time is up. Thank you very much for that. Listen.
Thank you very much. Are there any questions or comments? Oh, I have one question.
Yes.
You explained that one of the advantage of one generalization of dual algebra is it has some geometric meaning. What is it?
I didn't written down, but the essence is this formula, and so how to say, the geometric meaning is so this is n is the n's product ofそうかな。We consider the following geometry. The usual vertex algebra theory works on the complex plane, complex number plane. But instead, we can consider some conformal field theory on the torus. So given vertex algebra B, and also we can map, we can push this given vertex algebra to some new vertex algebra or conformal field theory on torus T. And this formula this formula gives in the operator product expansion on the torus, not on the original component. So we employed some coordinate transformation. The parameter the original definition, the full definition contains parameter gamma. This gamma is a modulus of the elliptic torus gamma.
What do you mean by nth product?
Yeah, nth product.
What is nth?
So
you mean original, the nth product in the original true algebra?
Yeah. So nth means that easy.
Yeah. Yeah. Mhm. So the idea is we consider the vertex operator algebra on the torus.
Yes.
That is the point.
Yes, this is the point.
Uh-huh. Uh-huh.
On the torus, we have new coordinate, say W.
Yeah.
And expanding in the new coordinate.
But on the torus, I mean, such kind of expansion doesn't make sense, right? Such kind, usually we write down some power series, Lorentz series, but on the torus, I don't think that such kind of expansion has meaning on the torus.
Torus has a global coordinate.
Yeah, global.
Yes.
Uh-huh.
Explicitly, something like this.
That is what appeared in the definition, in the
Yeah.
residue. I see. Thank you. Any other question? Comments?
Yeah, can I ask a question?
Yes.
So you were saying Huang's original definition of Juice algebra already used some kind of a genus one properties. And I think so is your generation, right? To a super conformal or super vertex algebra. So this genus one property remain to be the same, or well, to be honest, I'm a little surprised. So I don't know what's the right question to ask. So is it possible to see it from from operatic point of view? Is that to generalize Juice algebra to be some kind of a um, I don't know, a generalization of traditional spherical partial operator algebra? Is that possible to interpret the Juice algebra in certain way, geometrical way to make it an algebra over a certain operator?
Can you hear me?
Okay. I'm afraid that the answer was not. I think the microphone on Nagoya side has some problem.
Sorry. Let me explain again. So,
Uh.
I can tell you we have the relation isomorphism between the Hochschild homology through algebra and zeroth Kähler homology on the nodal curve. And I expect that our Suji algebra fits in this picture.
Oh, I see. So, wow, this is indeed possible. Okay, I see. I see.
Thank you very much.
Any other question? Okay, so if not, let's thank the speaker again. Thank you very much. So the next speaker is Renta Yagi from Nagoya University. He talks, his title of his talk is The Hop Superalgebras of Two-Colored Graphs. So please start.
Thank you for introduction. I'll talk about the Hop superalgebra of two-colored graph. This work is a joint work with Hattori Masamune and Shintaro Yanagida. So its contents. First, I introduce the non-super case of Hop algebra of graph. Let K be a field and G be a simple graph. And by bracket G, it means equivalent class of G. And by masker G, it means a linear span by bracket G. And by this product and products, and you are option, masker G become Hop algebra. It is called chromatic Hop algebra. The one fact is known. Let K be field and A be a commutative connected graph graded Hop algebra, and zeta be a character from A to K. And lambda be the ring of symmetric functions, and zeta lambda will be x1 to 1 and other variables to 0. Then there uniquely exists morphism of graded Hop algebra phi such as this diagram commutes. So Hop algebra of graph is commutative by this switching, and masker G has gradient by the number of vertex. And G is connected. So there is a morphism from G to lambda. The image of phi is called chromatic symmetric functions. So our main question is, can we make chromatic symmetric functions in superspace? So at first, we introduce superspace and Hop superalgebra. Vector space V is called superspace if V has a z over 2z graded. The notation V0 means even part of V, and V1 means odd part. And linear map from V to W is even when the image of even part is in even part of W, and odd image of odd part is in odd part. Odd linear map is defined as similarly like that. A superspace has some properties like these Cauchy roots. So Hop superalgebra, we define the Hop superalgebra. The Hop superalgebra is a Hop object in the category of superspace. Next, we introduce symmetric function in superspace. Let xi's be even variable and theta i's be odd variable. So theta I, theta j equal minus theta j, theta I. And a symmetric group sigma acts like that. A permutation of variables. And kx theta n Sn be the ring of symmetric polynomials in n super variables. And kx theta n Sn and m means the space of homogeneous elements with degree of x is n and degree of theta is m. by projective limit, we define the this asymmetric function in superspace. To write the symmetric function in superspace, we define superpartition. Lambda be a superpartition. It means that from lambda 1 to lambda m is in integer greater than 0 or equal to 0. And lambda m plus 1 to lambda n is in integer greater than 0. We call m fermion degree of lambda. And this is called total degree. For superpartition lambda, we define the monomial in superspace like that. Especially ER is this, and E to the S is this. Example M021 is this polynomials, super polynomials, and M121 is this. Add red variables in M021. Next, we explain combinatorial Hopf superalgebra. Combinatorial Hopf algebra is a pair of Hopf algebra and character. So we have to define the super character to the super analogy. Let epsilon be odd element. So it means that the square of epsilon is a Gaussian field. Epsilon, we define this. Then for Hopf superalgebra H, zeta is a super character. If zeta is even, an even map, and zeta satisfies this. When H is a connected graded Hopf superalgebra, we call pair HZ combinatorial Hopf superalgebra. A simple example is symmetric function in superspace. This super character is x1 to 1 and xn to x2 to xn to 0, and theta 1 to epsilon, and theta 2 to theta n to 0, and the coproduct like that. Our main theorem is that let LZ be a commutative combinatorial Hopf superalgebra. Then there uniquely exists a morphism of superalgebra psi, such that commute these diagrams. More explicitly, the image of psi we can write like this. In this expression, Z lambda is a composition this. A remark, so this proposition means that lambda xi S is the terminal object of the category of commutative combinatorial Hopf superalgebra. And more generally, we prove the quasi-symmetric function in superspace SQSIM is a terminal object of the category of combinatorial Hopf superalgebra. As an example of combinatorial Hopf superalgebra, we studied chromatic polynomial in superspace. Two-colored graph we defined. For finite simple graph G, we take a subset W. Then we call this triple VWE two-colored graph. V is vertex set set of vertices. So in this definition, V minus W mean black vertex and W mean white vertex. Example like this. Black is V minus W, white is W. Similar to non-super case, Pascal G dash, we define K-linear span by equivalent class or graph. And we define Pascal C, right? Ideal generated by this element. And we define Z by the quotient of Z prime by C. And then Z has by grading by the number of vertex and the white vertex. And Z is connected. And we, by defining product and coproduct, product is same to the non-super case. A coproduct like this. This is different to non-super. By this, Z is a connected, commutative, graded Hopf superalgebra. So we can use that theorem. Example of coproduct like this. So white vertex tensor one white vertex is 0 in Hopf superalgebra. By switching this tau. Next, to make the combinatorial Hopf superalgebra, we have to define the supercharacter of G. We define like this. If H set is empty and there is no white vertex, its value is 1. On the other hand, H space is empty and there is only one white vertex, its value is epsilon. Otherwise, then the pair G zeta ZCH is a commutative combinatorial Hopf superalgebra. So we can get a morphism from G to lambda. We call this image chromatic symmetry function in superspace. Example like this. Our calculation, we get some proposition. Let's Kn plus 1 be a complete graph such that the number of vertices in n plus 1 and the number of element of W is 1. And then its super polynomial is like this. A remark, when the number of white vertices is greater or equal to 2, the polynomial is 0. Because white vertex tensor white vertex is 0. And others has H, so the value of the supercharacter is 0. So and similar to the non-super chromatic symmetry functions, our super polynomial can explain by proper coloring, like this. A future of my research and my desires. First feature work, can we make LT polynomial in superspace? Second, what is super analog or chromatic quasi-symmetric function? A chromatic quasi-symmetric function is defined for the oriented graph. So it is a key to define ascent in the supergraph. Third, there some relation between affine Hecke algebra and chromatic quasi-symmetric function in superspace. For example, there is a Qt chromatic symmetric polynomials. So I want to know whether we can make super analog or Qt chromatic. But affine super representation theory of affine Hecke algebra in superspace is I don't know. So I think it's very hard. Finally, can we make super analog or relation between chromatic quasi-symmetric function and class functions, or GANFQ? That's all. Thank you for listening.
Thank you very much. Any questions, comments? Can you show us your main theorem again?
Amazing. This.
And in your example, you take two colored plane graph
Yeah.
as data for A, right?
No. This theorem is generally Hop super.
Yeah, I understand. But in your example,
Yes.
in your
As an example, two colors.
so you constructed Hop superalgebra from two colored graph.
Yes.
That is an example.
Yes.
But your main theorem is more general.
More general. If non-commutative, SQ thing is a terminal object.
I wonder, so I mean, two coloring related to superstructure?
Two colors is
Black
the
and white.
superstructure in the graph.
Yeah.
I think.
How about we have more coloring? Three color.
Three color. So I don't think so. I don't consider, but I want to consider someday.
Or is there other way to construct Hop superalgebra? I mean, not from the graph.
I don't know. I know only graph. So
So only example
Only
is
example.
to define Hop superalgebra
Yeah.
from the colored graph.
Yeah.
I see.
So we introduced the color two notion to define the parity in the graph. So three or more colors. I can image more notion in the graph.
I see. Other questions? Comments? Okay, if not, let's thank speaker again. So we have 10 minutes break. The next talk starts at 50. Hello, Professor Kong. ないかな。Professor Kong, are you on Zoom?
Oh, yes, yes, yes.
Please share your screen.
Mhm. Uh, Wait a minute. How I supposed to? Okay.
Yes,
Okay, can you see now?
yeah, we can hear. We can see your slide. So in 2 minutes.
Okay. Wait a minute. How am I supposed to? Just a second.
Okay, let us resume the session. The next speaker is Liang Kong from International Quantum Academy, Shenzhen. Uh, he, the title of his talk is Topological Weak Rotation and Symmetric TFT. So please start.
Okay, thank you very much for having me just have the opportunity to speak here. Okay, so I'm gonna give a talk about some kind of a review of an old subject, which a work had been done a long time ago, but uh, but the reason can I? Oh, okay. The reason I talk about it is because recently there is a proposal of a so-called sandwich construction and also called the SIM-TFT, or some other people also call it topological holography, which was discovered in the high energy communities. It become a very hot topic in high energy theory and become a very fundamental tool in studying a general quantum field theory, even though the theory is gapless, and you can still use some kind of a topological method to study it. The basic idea is that it says that a gapless quantum field theory, let's say X and N is a space-time dimension, you can find a way to split the gapless phase into a sandwich. Okay, on the one side of the sandwich is a gapped boundary. It means topological boundary. Okay, in the bulk, it is a topological field theory. And on the other side of the other side of the boundary is gapless. Okay, so when you fuse them together, it's remain gapless. Okay, so the general terminology is that the gapped boundary encode information of a non-invertible symmetries. Okay, because it's gapped. It contains topological defects. They form some higher categorical structure, and the ingredients of the higher categorical structure are called invertible symmetries. And the second part is the gapless boundary. encode the information of the dynamic data. However, this splitting is a proposal. Um, it's not very detailed in the sense that what is the meaning of the gapless boundary is not so clear, even though the other two is maybe better understood. Okay, so in this talk, I'm going to show that this idea of SIMTFT is a consequence of mathematical theory of gapless boundary of topological orders, which was developed some years ago. And this theory provide a precise meaning of about sandwich expansion and even a powerful way to compute the sandwich. Okay, that's the purpose of this. All right, so let me tell you this briefly or very quickly. What is this gapless boundary theory of a gapless boundary of 2 plus 1 d topological order? So basically, what you do is consider a chiral gapless boundary. Okay, assume that the gapless boundary is chiral for now. Okay, but eventually we're going to give you a more general description of the gapless boundary, which could be non-chiral. Okay, but let's start for simplicity. Let's start with the chiral case. Let's consider a chiral gapless boundary of 2 plus 1 d topological order. Okay. In general, it was believed that the 2 plus 1 d topological order was described by a pair and C, and the Curly C is a multi-tensor category of anyons. Okay, so the anion in the 2D system form a multi-tensor category because it can be braided, can be fused and braided. Okay, and the small c is a chiral central charge. Okay. So now we want to analyze what is so you want to find the mathematical description of the chiral-gapless boundary, then it's better to analyze what are the observable living on the 1 plus 1 d worksheet. Okay, the conclusion we're going to draw in a few slides is it turned out that the microscopic observable on the 2 plus 1 d worksheet, sorry, 1 plus 1 d worksheet, it turned out it formed enriched fusion categories. Okay, this statement is very general. I didn't even say the 1 plus 1 d worksheet of the chiral-gapless boundaries. Okay, it means that this statement, okay, the microscopic observable on the 1 plus 1 d worksheet, regardless whether it come from a chiral-gapless boundary or some other 1 plus 1 d system, they always form enriched fusion categories. Okay, let's see why it's so. Okay, well, in general, on this 1 plus 1 d worksheet, what do you have? I draw in this picture. Okay, this picture show you that what could happen on this 1 plus 1 d worksheet. The most important data is that it has a family. Okay, it has a family, a set or the set of labels of topological defect lines. Okay, so you have a bunch of label for this defect line, and for each pair of defect line, you have MAB, which is the space of fields living on the zero defect junctions, as illustrated on this picture. Okay. In particular, or you can say that MAB is also operator that change defect line A to defect line B. Okay, so in particular, it also means that the space of field living on the topological defect line labeled by A is just MAA. Okay, so when A and B are the same, MAA is just the field living on a particular TDL, topological defect line. Okay, then it has OPE. What kind of OPE you have? Okay, so the most general OPE is of this type. It says that you can have a defect field living in the junction between B and C. Okay, and you can also have a defect field living in the defect junction between A and B. Okay, you fuse them by a OPE product, it then the fused field become a defect field living in A and C, right? That's reasonable, right? Because In the picture, you have just field living here, another field living here. When you fuse them together, it become a field living in between A and C. Okay, that's the most general OP you can have. All right, but if you look at this picture, if you look at this three data, you can see that. Wait, what kind of thing you have? You have a set of labels, and for each two label, there is a space, MAB, and then you can even fuse them. So these three data together already form a structure similar to a structure of category, right? What is category? You have a bunch of labels, label the object of the category, and for each pair of label, you have a space or harms, and you can even compose them. Okay, you're almost there, but still something missing. Something very important is the identity. So I'm gonna tell you the identity next slides. So here we go. There is a very special label called the trivial TDL. Okay, then the field living in M11. Okay, so one is a trivial TDL, and the field in M11 can live in two cells. Okay, so the field, sorry, the chiral field living in the two cell must be M11. Because why? Because what the meaning of a label is trivial? When the label is trivial, as shown in this dashed line, okay, in this dashed line, okay, the label is trivial simply means that it cannot be distinguished from its neighborhood. That's why it's called trivial. So M11 is exactly so M11 is previously M11 is the field living on the dashed line, but because it is trivial, so M11 must live in the entire two cell. Okay. All right. Another important information is that so perhaps I skipped a little important thing is that M1 living in two cell and is chiral, right? And the field cannot be have a monojomies, okay? And moreover, it so from already ancient time, I think in the early, I think maybe in the 89 or early 90s, is already know that there are VOA living on the chiral gapless age or chiral gapless boundary on the 2+1D topological field theory, because well, this is not something because I mean it's something that is well known. It's just people already believe that there is a CFT on the gapless boundary. Okay, let's also take that for granted. Okay, and then if M11 is a chiral CFT means that it is a VO mathematical terminology for that is a vertex operator algebra, which is already covered in the first talk in the afternoon. Okay. And so in a VOA, there is a subalgebra field generated by energy moment tensor. Oh, sorry. Yeah, in this case, it's chiral. So the Z bar is, it does not depend on Z bar. I should get rid of it. But anyway, so the energy moment tensor generates the subalgebra of M11, okay? And well, that just means M11 is a VOA. However, now maybe it's the first time I want to tell you what a topological TDL really is. Because in the previous slides, I said, oh, this is a topological defect line, but what do I mean by a defect line being the topological? The meaning for a defect line to be topological is that these the Isaba algebra generated by energy moment tensor is transparent, is necessarily transparent to the topological defect line. Okay, so that means the field can fuse into so the field generated by energy moment tensor can fuse onto the defect line, okay, from one side. So the field leaving in the field in M11, they can fuse well, no, sorry, not M11, but the very small subalgebra generated by energy moment tensor must be transparent to the TDL. Means you can fuse from one direction to MAA, okay, but remember that you can also fuse from the other way, right? These two must match. Okay, These two must match, not only match, they have to be embedding. Okay, so that means transparent. It cannot have any kernels. Okay, so it must be isomorphic to its image. So as a consequence, the field living in this subalgebra can move into the TDL and move out. Okay, that's very important. So, um, but in general, it's possible that you can have a subalgebra V. Okay, you can have a subalgebra V, which is a subalgebra of M11, but slightly bigger than the algebra generated by energy moment tensor. That at this stage, it just means we do not know which one we should choose. Okay, then we take that as a defining data of the whole setup. So that means if you choose your symmetry, the V can be viewed as a symmetry sometimes called chiral symmetry in the theory of in the community of CFT. People sometimes call it chiral symmetries. And when V is big, the number of TDL that is transparent to V becomes small. If you choose V to be small, for example, you choose to be the minimum, which is come from the subalgebra generated by energy moment tensor, then it allow more TDLs. Okay, so V really define what we mean by TDL. So without lots of generality, we just assume there is a subalgebra V which is transparent to all the TDL. Okay, and for the at this stage, actually, I do not need assumption, but just for convenience, let's assume V is rational. Okay, just for convenience for now. Okay. When V is rational, what do I mean by that? It just means that okay, the mod V is a modular sensor category. Okay, and this statement only depends on Morris-Seiberg theory and Huang's theory. I shouldn't cite my work because that's for previous slides. Only when the only when the age is not chiral. Okay, if the boundary is not chiral, you have to choose. You have to change M11 to be a different algebra, which is not a VOA in general. It is a full field algebra. It's a non-chiral analog of VOA. That's why I cite this. But if I assume it is chiral, I don't need it. Okay. So let's assume now is a V is rational VOA. Okay, so mod V is a modulus as a category. And what's the first statement we can make? The first statement I want to make is that MAB is clearly a V module. What do I mean by a VOA V? A module over VOA is actually it mean if you know the definition. I want to skip the detail. If you know the definition, then it simply says that this module not only have a left V actions, it actually have a two-dimensional V actions. If you familiar the Euro notion of module over VOA. Okay, well, mathematically you can describe it as MAB is simply an object in mod V. Okay, and the second, the compatibility between the OPE, okay, and the V action, okay, why there is a compatibility? What do I mean by this compatibility? Okay, let me show you what I mean by this compatibility. Think about a field living in a vertex operator algebra V, okay, and think about a defect field living in the junction MAB, and a defect field living in this junction MBC. Okay, so what do I mean by compatibility? The compatibility means that there are three ways to fuse them. Okay, the first way is that you let the field living in V first fuse with the field living in MAB, then fuse with the field living in MBC. That's the first way of fusing, okay? But there are three of them, okay, in total. The second one is, well, you let the V fuse onto MBC first, then fuse with the field living in MAB. The third one is you let the field living in MAB first fuse with the field living in MBC, then fuse with the field living in V. The three of them are compatible. That's exactly what is so-called so-called Jacobian identity for intertwining operator. Okay, so as a consequence, I wanna make this statement. So the compatibility between the OPE and the V action show you that this OPE must be a intertwining operator over V. But by the mathematical theory of the tensor category of a VOA, this intertwining operator is precisely equivalent to a morphism, okay, a morphism from MBC tensor MAB, but relatively over V. Okay, here's the difference because here this tensor product is over vector space. Is vector space tensor product. Okay, but here the tensor product is already become a over V tensor product. This statement, in order to make sense of the statement, I already need I should cite. I forgot the reference. I should cite. I used the. Yi Huang and James Lopolsky's tensor category theory of a VOA. And Huang is the same guy in the first talk of juice algebra in the first talk in this afternoon. Okay. Okay, so this is the well-known result. But as a consequence, you see MAB now become object in mod V. And what happened to this now? MBC is object in mod AB, is in the mod V. So it's a V module. And MAB is also V module. Together, because there is a tensor product relative over V, together it's still altogether it become the tensor product is also a object in mod V. Okay, so the since this is a object in mod V, and MAC is also object in mod V, then you can say that we can have a map, and this map is a morphism in mod V. Okay. So this is a highly non-trivial statement, okay? But if we agree on that, so all the MAB is object in mod V and all the composition is a morphism in the mod V. As a consequence, we simply obtain an enriched category, a category which is enriched in mod V. I said it is an enriched fusion category. Why is a fusion? Because they're horizontal fusions. Okay, so the tensor product of TDLs I showed it here. So you can have a TDL right labeled by A. You can have a TDL labeled by P. Right. And if you horizontally fuse them together, you got TDL labeled by A tensor P. So this upgrade, so this horizontal fusion upgraded the enriched category to an enriched fusion category. Okay. You can say or enriched monoidal category. However, the reason I said is fusion is because, well, it's just everything is a semi-simple. Okay. Everything is semi-simple. Yeah, we just call it fusion. You will see why in the next slides. The important information I want to emphasize here is that all the correlation functions and OPE among the defect field can be recovered from this pair, okay? Simply from this pair. And this statement is also heavy loaded because I have used many results in the field of VOA to make sense of this statement. Okay, so yeah, but I ask you just trust me. Okay, okay. So I give a very detailed analysis of the observable on the worksheet. Now let me draw to the conclusion. So the conclusion, there is a small gap in the logic. So I wanna just jump to the full conclusion now. So the so-called rational gap or gapless boundary. So you see here, I'm going to give a statement of the boundary of 2 plus 1D topological order, again, given by the pair C and C, but the boundary now become either gapped or gapless. So what I'm going to describe to you now is a mathematical characterization of both gapped and the gapless boundary of a 2 plus 1D topological order. Okay, it's completely characterized by or classified by a triple. Okay, what this triple is. First, it's V. Okay, what is this V? V again is here. Okay, V is a subalgebra of M11. M11 is the field living on the two cell on the worksheet. Okay, when the boundary is a chiral gapless boundary, V is a rational VOA of central charge C. Okay, when the boundary is non-chiral gapless boundary, V is a rational full field algebra with chiral central charge. Okay, as a C. But when the V is trivial, so C can be viewed as a trivial VOA or trivial full field algebra, which is given by the complex numbers. Okay, then it describes a gap boundary. Okay, the second data is a fusion category equipped with a braided equivalence. Okay, and once you have this S, then so if you have this equivalence, okay, then you can you well, this is a little technical, but okay, you can have a braided equivalence between mod V bar. What mod V bar? B bar just means change the braiding to anti-braiding. So there is equivalence between mod V bar and B. Mathematically, just corresponding to because this condition. Okay, so mod V bar is simply the relative, what do you call it? Okay, Mueller centralizer, or is the Mueller centralizer of C in the dream field center of S. This part is a little technical, but I'm gonna explain the geometrical meaning of it in the next slides. Okay. So no matter what, because B is just mod V bar, okay, so it acts on S. So which determines, what I wrote here is that it determines the B action on S. As a consequence, there is a B enriched fusion category defined by the so-called canonical construction, which means MAB is precisely given by the internal Hom of AB and as an object in B. So AB are object in S. The internal hub is an object in B. Okay, it's a standard construction, which people know a long time ago for enriched category. Okay, so an important result of this classification is that even though you gotta enrich the fusion category, which is given by B and S, right? There is a notion of again a monoidal center of this enriched category, and you can show that the center of this enriched category is precisely the bulk C. Okay. So the phi, this relation here looks a little mysterious, and also this one looks a little mysterious. Now I'm going to give you a geometric interpretation of that. So let me reinterpret what we have in the previous theorem. Let me restate it. So it says that a gap and a gapless boundary of a 2 plus 1 d topological order can be completely characterized by a pair. Okay, the first data is a V and the braiding. Okay, the phi is the braiding. Okay, a braided equivalence. Okay, okay. These two data can be called local quantum symmetry. It provides information of the dynamical information of the quantum field theory that control the correlation function, that kind of thing. But the second data and the B and S are completely categorical. Okay, so this B is again the Mueller centralizer. It's completely categorical and complete topological. Okay, if you just focus on this what I call topological skeleton of the phase, it's obtained by the following mysterious process. Okay, the first it is the topological data have an algebra data which is enriched fusion category. Its monoidal center equal to the bulk. Okay, but how to determine this X topological? Well, you just start with a physical situation. Okay, the first you have a 2 plus 1 d topological order. This is in the spatial dimension. Okay, this is I draw it in the spatial dimension, and the CC is topological order, and the BC with the same central charge represent another topological order. Okay, and such that they share a gap domain wall between them. These conditions, so this physical configuration is precisely this mathematical statement that the C and the mod V bar is Brady equivalent to the center of S. So this this Brady equivalence is precisely can be reinterpreted as a physical configuration that the BC and CC is separated by a gap dilemma. All right. Everything is topological. Everything is gapped. Everything is topological. Okay. But now what you do, the magical thing is that you rotate this physical topological order to a vertical direction, which represent a virtual topological order, which doesn't exist. It's something living in the you got something living in the space time. It's just a way of a bookkeeping. At this stage, it looks like a bookkeeping device. Just tell you, oh, this B and S must combine in a way to form a enriched fusion category. Okay, so in the next slides, I make it even more explicit why I want to do that. So this is, oh, by the way, this process called topological weak rotation. Okay, so let me restate what it means. You rotate it to the time direction, and this BC looks virtual. It become a background for the space-time. So it is a bookkeeping device at this stage, right? To summarize the observable on the worksheet. Okay, this BC is not the physical topological order anymore, but it serves as a mysterious internal symmetry of the space-time background on the worksheet, 1+1D worksheet. Okay, and in particular, it provides holography duality because when C is trivial, when CC is trivial, what happened? When CC is trivial, and this B must right, the CC is trivial, and this B must equal to the center of S. Why is that? Because this condition. When B is trivial, B is mod V bar. Okay, so that means if this is trivial, oh sorry, when C is trivial, then this mod V bar must be the Drinfeld center of S. But remember, B is just mod V bar. Okay, so B must equal to the Drinfeld center of S. So in this case, when C is trivial, well, the CC is gone and the CC is gone. After you rotate the time direction, you simply got 1+1D without any bulk. Okay, so in this sense, we obtain holography. It's a holographic duality of 2D theory, a 3D theory, a 2+1D theory. Okay, this is 2+1D theory. But after you rotate to time direction, you get 1+1D. Okay, so that's a 3D theory and 2D theory duality. Okay, this is some called the topological holography. All right, let me give you some examples. So first example is that, well, if the topological order is non-chiral, and you can have what describe this pair. So it means the chiral center charge is 0, and the module sensor category is the Drinfeld center of a fusion category. A is a fusion category. Okay, and then if this is the case, the pair C and A describe the gap boundary. C is the V because, as I said, when a V equals C is gapped. Okay, so yeah, so when C is a C and the mod C just a category vector space, a finite dimensional vector space, right? Okay, so it describes the gap boundary. And when the bulk is E8 invertible 2+1D topological order, it means that, okay, C is a still trivial one, the vect, but the chiral central charge is non-trivial, become 8. In this case, the VOA come from E8 VOA, and the enriched category is still the VAC enriching VAC is still the VAC. Okay, so in this case, it defines a non-trivial gapless boundary. I think this is what make it a non-trivial. You know, its central charge is non-trivial, but the topological order is non-trivial because its gapless boundary is non-trivial. All right, similarly, let's consider V is a rational VOA such that the C is just a multi-system category defined by mod V. Okay, if this is the case, and we can show immediately the pair V and C enriching C define a gapless boundary. Notice here I already get rid of the data of phi, but the phi is just this. Let me say it again. So phi is a relation between these two. Okay. Oh, sorry. I think I shouldn't use phi. I think I used this one. Okay, so I shouldn't. I should get rid of this phi. This phi. What I mean by that, it just mean this one. The isomorphism between B and mod V. All right, I already get rid of that. Well, just remember that's the data. So C is just the mod V. Okay. In this case, phi is identity. So it defined a gapless boundary of CC. Why? Well, because well, you're checking all you need, and this is just one example. And in this case, it's particularly interesting because it shows that there is a monoidal center of this enriched category give you the C. This solves a very old mathematical problem people already asked in the middle of 90s that can you find something whose Dreamfield center or some kind of center equal to C. Okay, this actually give a solution to that equation, and the very simple solution because what is a C enriching C? Okay, the C enriching C they have the same set of object. The only thing you do is just replace the harm space, okay, by internal harms. That's all. Okay, just replace harms by internal harms. Then you got a solution to this equation. Okay, and similarly, I can give you some other example. For example, the triple, this triple, then so the local symmetry, what we call local symmetry now is replaced by V tensor V bar. That's an example of a non-chiral symmetry. Okay, in this case, um, this pair define an anomaly-free 1+1 DCFT. Okay, because if you compute well, anomaly-free simply means that it's not a boundary of anything, or it is a boundary of the trivial phase. Okay, because when you compute the Dreamfield set, well, not Dreamfield, the monoidal center of this enriched category, you got a category of VAC. Okay, there's no there's no bulk topology order. Okay, so that's why I define an anomaly-free 1+1D CFT. In particular, if it is anomaly-free, and you can check the field living on the trivial TDL, which is just internal harm, and if you compute it, it's precisely the famous modular invariant partition functions. Okay, and of course, this very powerful. This theory powerful is that you can also compute all the TDLs using internal harm. Okay. All right. Um, it's tempting to give you more example, but I don't think I have time for that. So let me skip it. Okay. So the idea of the sandwich construction of CMTFT naturally follow from this theory as a consequence. For example, if you our discuss the holographic case, right? The 2+1D topology order with a gap boundary S. Okay, so B now equal to this. If you do a topological weak rotation, you got that. It's become a 1+1D gap phase. Okay, or gap is CFT if you want it. Okay, so this is holographic. Then how to expand it as a sandwich? That's very easy. It's already appeared in our 2017 paper. You just drag this blue line horizontally to get a gapped boundary, and in the middle, what do you get? You get the Dreamfield center of that, which is topological. Okay, but then this theory provide you a precise mathematical description of the so-called dynamical boundary as originally proposed by Gaiotto and Galp in 2020. Okay, so now this theory provide you how to describe this dynamical boundary. Okay, this is a symmetry boundary is here, and in the middle is a CMTFT. Okay. So this sandwich construction or SIMTFT is a consequence of our much more complete theory, and we also provide a complete mathematical description of the dynamical boundary, and we want to show that our theory is much more powerful than sandwich construction. Let me show you. You probably wonder, oh, why you don't just use sandwich construction as other people do, and why you want to rotate it to time direction? Okay, there is a reason why we do that instead of using sandwich construction, because sandwich construction I think is only part of our story, it's a consequence of our story, but we do not want to use it because in the next slides I'm going to show you why it is powerful. Because by the folding trick, oh sorry, by the folding trick, you can consider a gapless domain wall between two topological orders, okay, with different central charge. Okay, for example, this is a topological order with a central charge, and now this is another topological order with a different central charge, and the gapless wall is defined. This define a so the vertical one together represent the gapless wall. Why is that? You can use folding trick. By folding this D to the other side, then this become a gapless boundary, right? So the gapless domain wall and the gapless boundary is the same thing by using folding trick. So the vertical one, this vertical triangle represent a gapless wall between two topological order. Similarly, you have another gapless domain wall between these two topological order. Okay. Now the question is, can you fuse this two gapless wall? Yes, the fusion formula is almost tautological. So what are you gonna do? Okay, you have a something this cache encoded dynamical data, right? U and V. When you fuse them, in the middle it's totally empty. Okay, you just fuse them as a vector space tensor product. Okay, and what is A and B? Well, you see they fuse tautologically in the middle, right? I mean, there are nothing in the middle. So you just fuse them as a Deligne tensor product, as an obvious stacking two topological order. That's basically okay. And what's in the bottom? You have M. Okay. In the bottom you have M, you have N, and you have to fuse along D. Okay, you have to fuse them along the D. You got this formula. Okay, and this become a very powerful formula. Okay, the reason I'm showing you is that consider 2 plus 1D topological order with canonical gapless boundary VCC. Okay, it's the C enriching C. Okay, and the C is just mod V. Okay, so again, so V is a VOA and the C is mod V. Okay, this describes a canonical gapless boundary of the topological order. So I showed them. Okay, so on the one side it moved this way, on the other side move this way. Well, if you have a if you draw the circle, then they will connect together. Okay, now what do you do? Okay, you can also introduce a gap domain wall between CC and the CC. Okay, so this M is a gap domain wall between the CC itself. Okay, so it's a codimension 1 defect in the CC. Now you fuse them together. Previously, physicists already argued that if you do that, you got something modular invariant CFT. But now you don't need the gas, you don't need the physical argument. You just use naively our formula. We provide the formula for you, right? You just use this formula, fusion formula, the fusion formula provided in this and in this way. Okay, just use it naively. You got this formula. All right. Okay, then you compute. So you got an enriched category. So M is enriched in CC bar, and you can compute what is leaving on the two cell. Okay, you compute that. The field content leaving the two cell is M11. Okay, which is by definition is internal harm, leaving in the C and C bar. And if you compute it carefully, as we have done over here, that's another example here. Okay, that we showed in this example. Okay, that you give you the diagonal. But if you give you if this is non-trivial M, yeah, it give you an all the modular recover all the modular modular invariant partition functions canonically associated to M. And in particular, this established a one-to-one correspondence between the gap domain wall between 2 plus 1D topological order of that, right? M is a gap domain wall between the itself, between the CC itself, and the modular invariant CFT extending V tensor V bar. This one-to-one correspondence was known a long time ago, but without really understanding why this is true. Okay, there is a mathematical proof. It was known a long time ago. Okay, modular invariant CFT extending V tensor V bar was known to be a Lagrangian algebra in C bar. Okay, and it's just one-to-one corresponding, and it's known that it's one-to-one corresponding to the indecomposable V module categories, and it was proved to be a gap boundary of this double layer system, and it's bifolding trick is equal one-to-one corresponding to the gap domain wall. This result was known a long time ago, but not only now, by looking at this picture, we provide a physical proof of this statement. Okay. Oh, my time is almost gone. Let me just summarize. So this topological weak rotation can be generalized to all dimensions. Okay, so it means that any quantum liquid which is gapless, could be gapless, are always split into two data. One is controlled dynamical data, we call the local quantum symmetry, another called the topological data. And the topological data, again, you can use topological weak rotation to obtain the topological data of a gapless boundary of any topological order in higher dimension. We propose that. Okay. Well, actually, we also have a theory, mathematical theory of the dynamical theory. Okay, which is based on which is called the theory of topological net, generalizing the mathematical theory of a conformal net in 2D. But I don't need to discuss that. Okay, brief comment on this holographic duality was also discovered by many people from different contexts, but perhaps our discovery is among the earliest. Okay. Anyway, so this picture also tell you our theory not only tell you that you can split into a sandwich, you can split the gapless fits into a sandwich. This theory also tell you how many splitting you can have. Okay, you can have infinitely many of splitting parameterized by a monoidal functor to the data S from another fusion n category to a fusion n category S. As long as you have a monoidal functor, you can do that. Okay, the particular one physicists have in mind is really the canonical one, is the identity functor from S to S provide a sandwich construction. Okay, so it tell you that our theory were able to say more about the sandwich construction. Well, here is more. So after this theory was established, a lot of more you can say, and I think the most advanced result is that you can even compute the category of top quantum liquid, no matter it's gap or gapless, and it turned out this category is surprisingly simple. Okay, so let me draw the conclusion. So my goal of this talk is to promote the idea of a topological weak rotation, which is much more complete than the idea of the SIMTFT or a sandwich construction topological holography. It allows you to do a very explicit computation of sandwich construction, and okay, yeah, I think that. Well, okay, the last sentence maybe. So although the topological skeleton is not enough to determine a gapless quantum phases, it's already provided sufficient amount of information to study questions such are irrelevant to the missing data, such as boundary-box relation, Morita equivalence of two boundaries, duality, holography, and the computing dimensional reduction process, or even the studies the condensation and phase transitions. And they provide a serious constraint to the dynamic data. So we believe that this really provide a new insight to study gapless quantum field theory or gapless quantum field theory altogether in a single unified framework. All right, thank you very much. Sorry, I've been over time.
Oh, thank you very much for a nice talk. Are there any questions, comments? So from Nagoya, we have question.
Thank you for your very nice talk. And I have
Thank you.
please explain. So in the page 8, you explain some examples of boundaries.
Maybe this one?
Very interested in these examples. And in the item 2, so there is some very special central charge 8.
E8, you mean this
Please
one?
explain, so why the central charge is such special one?
Sorry, what's your question? I didn't hear very clearly.
Yes, you can hear me?
Yeah, yes, now, yes.
The central charge is very special.
Yeah.
Can you explain the
Oh, why is it special? Okay. So this example, I just want to show that this theory was capable of describing a highly, yeah. So there is something called the invertible topological order. In particular, in the chiral central charge, the chiral central charge is 8, but the category of anion is trivial. It means that there is no anion in this case. So in the 2 plus 1D topological order, this 2 plus 1D topology is called invertible. So the only macroscopic characterization of the phase, non-trivial characterization, is the chiral charge. There's no anion in it. So it's almost trivial, but it's turned out it's not trivial because it has a non-trivial boundary because you can define a pair, and with this pair, the dynamical data of the gapless boundary is the EA VOA.
It means that affine vertex algebra or
Yes.
affine.
Yeah.
I see.
Yeah.
Not lattice vertex algebra.
Our fine one. Well, sorry. I think this is EA lattice. It's not our fine. I think it's EA lattice.
Yeah, because the central charge is 8, so a little bit.
Yeah, it's a central charge. 8 is quite special. All the 8 multiple 8 is, for example, when you can triple 3 times, you got a 24, and then you can choose this V to be a monster moonshine. So invertible 2 plus 1D topology always have the central charge, which is a multiple of 8. Yeah. For example, when I think for central charge 8, you only have E8. I don't know any other example, but for central charge equal to 16, you have 2, at least 2, I think. But for 24, you have more. I think that's already classified or something. I don't know. In the VOA community, there are more than 70s in one central charge is 24. But to answer your question, yes, in order to if you only want to focus the study of invertible topological order, the central charge is necessarily a multiple of 8. Yeah, this example just to show you that this theory was capable of catching the non-trivial gapless boundary of invertible topological order. That's all, yeah.
Okay, other questions? No. Yeah, I have one simple question. I would understand the topological weak rotation. Can I understand it as just making a time direction to spatial?
Right.
But
I would say at this stage, I would
why
say,
you have to take time direction to make weak rotation?
why is it called a weak rotation? Because on the left side, I completely ignore the time. It's only spatial dimension.
Yeah.
So I should say that. So on the left is 2 plus 0. On the right is 1 plus 1. This is 1
Yes,
plus
but in the bulk, you choose time direction, right?
In the bulk, no.
In the bulk,
For the bulk, I didn't draw at the time direction. Everything here is spatial. Everything here is a spatial.
All the spatial.
Yeah, they are spatial. I draw the 2 plus zeros here. It's on the left side. This is 2 plus 0. This is 2 plus 0. I didn't draw the time at all. I intentionally ignore the time. But on the right side, I intentionally rotate this to the time direction so that it means that B will serve as something very mysterious background for the space-time. As a consequence, you got an enriched category, and this enriched category mysteriously encode all the observable living on the space-time.
Okay, I understand. So originally, we don't have any time direction. But
Right.
after the weak rotation, we have one time direction. That is the vertical one.
Yeah.
Is that right?
Yeah.
Okay. Thank you.
Well, I have to say this is mysterious. People questioned why you want to do that. Why you don't let it down. But if it light it down, you basically what you do is similar to what other people did. You just look at this picture, okay? But the last picture, okay, do a sandwich construction. But what the whole story I'm telling here is that no, you should do this mysterious rotation so that the whole thing become much more powerful for you to compute. If you just using sandwich, you won't be able to see this formula anymore. Okay, you won't be able to see how this become this. Okay, so that's the power of this rotation. Yeah, I didn't tell you other powerful things to do. I mean, I missed a few slides. I can even tell you that the topological region is much more powerful in the sense it's functorial. Okay, it's not the sandwich. So that's why we never invented the CMTFT language because CMTFT for us is just a tiny special case of a much more general theory. And CMTFT is only a special case of this one.
Yeah.
But there are much more.
Topological rotation is more general than the sandwich construction.
Right. It's much more general.
Okay,
More
understand.
complete. Yeah, it's more complete.
Yeah.
Yeah. You. Yeah. Thank you for your question.
It's time is over, so let's thank speaker again. Thank you very much.
Thank you very much.
Please wait a few minutes.
フルスクリーンしてからシェアしたら選べないんですね。これまで選んで、それで入って、これでもいけますけどね。フルにした方がいいですか？はい。フルにします。するとなんか、こっちがわかんないけど、あれ一回切った方がいいですね。これもだ。シェアを切るべき。ズームが切れてる？ズームは入ってる？あれ？でもう一回シェアします。これで、はい、これでフルスクリーンにしたいんですが、フルスクリーンしようとすると切れます。なんでかわからない。はい、じゃあ、で、普通に。で、それで、切れるんですね。はい。
はい、これで大丈夫です。はい。
So the last speaker of the afternoon session is Masashi Hamanaka from Nagoya. He will tell us ADHM construction of instantons. So please start.
Yeah, thank you for the introduction. So first of all, I'd like to thank the organizers for giving me an opportunity to have a talk here. In fact, マイク入ってないですか？大丈夫ですか？はい、はい。Can you hear me? It's okay?
Yeah, okay.
Okay. Yeah. In fact, last month, I suddenly asked by Yanagida-san to give a talk in the end of August, I remember. But then I realized I will be quite busy in September, and and actually two days ago I had to give a talk on ADHM construction in Tokyo, and so I finally decided that I give a review talk of ADHM construction in Stanton here as well. So this is an introduction. So today I'd like to discuss instantons. There are global solutions of anti-cellular Yamil's equations with the finite action boundary conditions. So this is actually very important and plays very important roles in quantum field theory and geometry and so on. And the ADHM construction is a powerful method to construct the instanton solutions. It is based on the one-to-one correspondence between the modular species of instantons and ADHM data. And this story is very, very old, but still very, very important. So this is, in some sense, some milestones in the 17th or 18th gauge theories. And anti-self-Riemann equation is defined as follows. This is in 4 dimensions, in the Euclidean 4 dimensions. And today, I assume the gauge group G is UN. So the anti-self-Riemann equation is specified by the anti-self duality in the sense of hot dual, or the curvature F mu nu. This curvature is defined as follows. And this A mu is called the gauge field or connection. And now gauge group is UN, so the both F mu nu and A nu take values in n by n anti-Hermitian matrix. And this is a real representation. And in complex representation, these can be written as follows. And there's also important object, instant number, which is defined as follows. So this is the second Chern number actually, and take values in integer. Okay, so this is a simple preparation. And from now on, I'd like to discuss the ADHM construction of instantons. Instanton is the solution of this self-Riemann equation with finite instanton number condition. This is equivalent to the finite action conditions. Okay, so I'd like to discuss this construction. So as I mentioned, this is based on the duality between the instanton modular space and the ADHM data modular spaces. So this is denoted by blue and red. And actually, they are the one-to-one correspondence. And now, gauge group is assumed to be UN, and the instanton number is K. And they are the gauge transformations as usual. So the modular space is defined by the solution space modulo the gauge degree of freedom. So this is the left side. On the other hand, right-hand side, this equation is called the ADHM equation. So this is just a matrix equation, and k by k matrix equation. And originally, in the left side, this is a n by n partial differential equation. And this looks much easier to solve. And this solution is called the ADHM data. And there is a dual gauge, in some sense, gauge degree of freedom. And the modular space is also defined in right-hand side. And the right-hand side is much easy to solve. And there is one-to-one correspondence. So we can construct the instanton solution by solving this matrix equations. And furthermore, there is a duality map between them. And this duality map is also matrix equation from ADHM side to instanton side. So we can get instanton by just solving matrix equations only. But you may wonder why these modular space are equivalent. So this looks different. So today I'd like to discuss the one origin of this ADHM duality from the viewpoint of Fourier-Kynam transformation. So this Fourier-Kynam transformation is based on the following beautiful dualities between instanton modular space on 4 tori and instanton modular space on the dual tori. So the left side is an instanton on the 4 tori. And the gauge group is UN, and the instanton number is K. On the other hand, in the right side, we consider the also anticellular damage equation on the dual tori, but the gauge group is UK, and the instant number is N. So the rank of gauge group and instant number is exchanged to each other. So under this setting, there is a one-to-one correspondence between the modular species. And the dual torus is has opposite radius of the original torus. So if I write the torus is S1 times S1 times S1 times S1 times, and so each S1 have the radius R1, R2, R3, R4. Then the dual torus have the radius 1 over R1 and 1 over R2 and 1 over R3 and so on. So if the original torus becomes large, then the dual torus becomes small. Okay, anyway, this is a very, very beautiful duality. And there is actually duality map from right-hand side to left side. So I'd like to explain this one. The key, okay. So the duality map is defined by the Dirac equation. So now let's discuss the step from the right side to left side. So in the first step, we have to solve the dual anticellular damage equations. So now we assume to get the solution of the dual instanton. This is a k by k gauge field, this one. Now the local coordinate is denoted by x mu for original torus and xi mu for dual torus. And in the second step, we solve the following Dirac equation in the background of the dual instanton as follows. The detail is not important, but the solution is denoted by large V. This is Dirac zero mode. And in fact, in this Dirac equation, there is a parameter x here. So the Dirac zero mode depends on both xi and x. And now we assume we can solve this equation and get the solution large V. This is a 2k by n, because this equation, this part is 2k by 2k. And there is a family index theorem which guarantees that there is a large n independent solution of this Dirac equation. So this large n just corresponds to the instant number, actually. And finally, in the third step, we can construct the instanton, the original instanton on 4 tori by the bilinear of the Dirac-Zell mode as follows. So this inner product shows the integration of over dual torus, and this part is a V dagger del mu V. So V dagger del mu V gives rise to n by n matrix because large V has a n independent column, independent solution, and which is arranged the n columns. So this is n by n. And actually, this gauge field automatically satisfies anti-Cellarium equations, and the instant number can be calculated to be k, actually. So in the inverse construction is similar. So in the first step, we get the solution of instanton from left side. And in the second step, we solve the Dirac equation in the background of the original instanton. Then we have a Dirac-Zell mode, which is 2n by k. So this k is guaranteed by index theorem as well. So then in the third step, we can construct the dual instanton by the bilinear of the Dirac-Zell mode psi. So this gives rise to k by k gauge field, and so on. So in this way, we can prove the one-to-one correspondence between the instanton and the dual instanton on tori. So this is a very, very beautiful story. But this duality is just beautiful and not useful to construct the original instanton from the dual instanton, because the difficulty to solve is the same on both sides. So this step is the more troublesome. If we want to get the original instanton, then we just solve this directly. So if start with the right side, we firstly have to solve the dual instanton solutions, and furthermore, we have to solve the Dirac equation. So this is quite troublesome. But if we take some limit of the radius of the 4 tori, the situation drastically changed. So now let's take the following limit, that for a radius of the original torus to be infinity. Then original torus becomes larger and larger, and finally to be R4. And on the other hand, the dual 4 tori becomes smaller and smaller, and finally to be 1 point. So then this duality is between instant homogeneous space on R4 and instant homogeneous space on 1 point naively. Then let's return back to the construction. So firstly, we have to solve the dual instanton solution I mentioned. But now, dual torus becomes 1 point. So the differentiation have no meaning now. So naively, we can drop out this derivative terms, del mu, a mu, and so on. So then, dual instanton solution, dual instanton equation, the anti-Cellarium equation becomes just a matrix equation. Only this term only. And in the second step, originally this is also differential equation, but now derivative have no meaning, so we can drop out. Then this Dirac equation becomes also a matrix equation. Then finally, we can get the instanton solution on R4. So we can get the non-trivial instanton solution on R4 by just solving matrix equations and matrix equations. So this is the spirit of the ADHM construction. So let's return back to the one-to-one correspondence. Now we can understand why there is a commutator of the B1 and B2. So this B1, B2 is a K by K matrix. So this is just the A mu tilde and A mu tilde In fact, this is k by k. So essential part is reproduced by this naive observation. But in fact, in ADHM equation, there is additionally rectangular matrix I and J appear here. So this is additional ingredient. Yeah, because the previous discussion is too naive. We just drop out this part. But physicists expect that this part might give rise to I and J because AMU tilde is originally constructed from the original side by the bilinear of the Dirac zero mode here. And psi is essentially n by k and k by n and so on, the bilinear. So this part exists here. So before the dual torus shrink to be 1 point, there might be the contribution from this derivative part, and perhaps becomes this II dagger and J dagger J. Physicists expect, but there is of course no rigorous proof. But anyway, essential aspect is a zero-dimensional self-Yarmid equation. This is the ADHM equation. And actually, we can prove the one-to-one correspondence between instant moduli and ADHM moduli in the similar way as norm transformation. So actually there are other limits and other related works. Now, if we take the 3 radii to be infinite and the remaining 1 radius to be 0, then the original side becomes R3 and the dual side becomes just R. So the original norm duality becomes the self-Yarmid on 3 dimensions and self-Yarmid on 1 dimension. The equation is actually the Bogomolin equation and norm equation. And by this duality, we can construct the exact solution of Bogomolin equation. This includes the monopole solution. So this is norm construction of monopole. And of course, there are many choices, and there are several works. So now let's construct the exact solution by using the ADHM construction for the simplest case. Yeah, but before that, I would like to comment on the non-commutative extension. In fact, in the ADHM equations, there appears the commutator of the coordinate, in fact, because in the ADHM construction, the Z and B always appear in pair, Z minus B. So the existence of commutator of B1 and B1 dagger implies the existence of commutator of Z1 and Z1 bar, actually. And in commutative spaces, of course, this is 0, and the right-hand side is 0. But in the non-commutative spaces, this becomes non-zero in general. So finally, I would like to mention this point again. So firstly, let's construct the exact instanton solution for n equal 2 and k equal 1, which is called the BPST instanton. And this is very, very famous instanton, one instanton solution. Firstly, let's solve the ADHM equation for k equal 1. This is actually perfectly trivial because this is k by k matrix equation. So now k equal 1. So the commutator part automatically drop out. So we can take this matrix B1, B2 as an arbitrary complex number alpha 1, 2. So the remaining task is to solve the I and J parts. And the solution is easily obtained as follows. So now, by using the dual gauge transformation, we can set this forms. So this is actually general solutions. now rho is a real parameter. Real parameter. And in the second step, we have to solve the zero-dimensional Dirac equation in the background of this ADHM data. This is also very, very easy. And finally, in the third step, we can construct the gauge field as a bilinear of the Dirac zero mode of V. And we can actually easily calculate it. And the final result becomes non-trivial. And F mu nu implies the anti-cellular symbol here. So we can find this F mu nu is an anti-cellular Yamil's configurations and can be plotted in R4. And there are famous physicist Polyakov, and when he faced this result, he said, so this is the first time that the abstract modern mathematics had been of any use. So this is actually very, very surprising. And the ADHM construction is not just a difficult abstract mathematics, but very powerful to construct the real instanton solutions and useful to analyze the quantum field theory and so on. Okay, so, and we can easily plot this F mu nu, this coefficient parts of F mu nu as follows. So we can read that this alpha corresponds to the position of the instanton and the rho to represent the size of instanton. So in general, this large B contains the information of the positions. So especially after diagonalization, this diagonal part becomes the position. And I and J contain the information of the size of the instanton. And now let's take the low zero limit. So we can easily find the low zero limit is a singular. This is a singular configuration. So this just corresponds to the singularity in the modular spaces. Because in the case of rho equals 0, the group action becomes non-free. The group action have the fixed point. Because rho equals non-zero, the group action have, as usual, it's free. But in the case of rho equals 0, the both of I and J becomes 0. So the group action have the fixed point. And the modular space have the G2 symmetry. The modular symmetry is described by the divided by G2 because this group action has G2 symmetry. So we have to divide this G2. So there are orbifold singularity here at the rho equals 0. And this corresponds to the singular configuration. This is called a small instanton or ideal instantons in the commutative space. But now let's move to the non-commutative spaces. As I mentioned, in the right-hand side of ADHM equation, there appears the non-zero constant zeta here. So now the solution is deformed by zeta. This is actually solution. So I becomes a little bit fat by zeta. So even in the low zero limit, this I is not 0. So in the low zero limit, the gauge group action is still free. So totally free. So the modular space have no fixed point, no orbifold singularity. So this gives rise to the resolution of the singularity in the modular spaces. And this corresponds to the regular configuration, actually. So this is just a U1 instant. So by the non-commutative space extension, the singularity is resolved and a new physical object appears. So this is one interesting story in non-commutative spaces. Okay, this is a comment on instanton modular spaces. So in the commutative spaces, there is a symmetric product here, and there is orbifold singularity and so on. And multi-instanton case, the singularity becomes more complicated. This symmetric product just corresponds to the configuration of the k size 0 instanton. So collision of the 0 size instanton give rise to the very complicated singularity in the modular species. But in the non-commutative species, this singularity is naturally resolved, and the symmetric product becomes a Hilbert scheme. So this Hilbert scheme part corresponds to the KU1 instanton, and this becomes a smooth, and there is no singularity, even in the collision process. And the dimension of the instanton modular spaces are easily calculated by just counting the degree of the matrix. Then we can get 4nk. So in the originally in instanton case, we need the index theorem to calculate the dimension of the model spaces. But in the dual side, this is just arithmetic. So elementary school students can calculate the dimension of the instant model space. So this is very, very great. Okay, so finally, I would like to mention the norm construction of monopoles. But I start 647 probably. 10 or 15 minutes remain. Okay. Okay, I continue. Okay, this is a duality between the Bogomon equation and norm equation. And the Bogomon equation is this one, the left side, and the norm equation is the right side. So this is a three-dimensional anticellular Yamada equation, and the norm equation is a one-dimensional anticellular Yamada equation. This one and this one. Yeah, this is B is a magnetic field. So yeah, actually, this is simply dimensional reduced version of the four-dimensional self-real Yang-Mills. But there is a additional boundary condition for Higgs field here, and the norm data here. This T is called the norm data. T is a K by K. And yeah, A4 is a becomes Higgs field large phi now. And now we focus on the G called U2 case. So this monopole is 2 by 2. The norm data is K by K. Okay, so okay, I briefly discuss the construction of the monopole from now on. So in order to do this, so let's go to the Kyoto now. So this is a norm equation and the Bogomon equation. And in fact, I would like to mention the deep brain interpretation of this norm construction, but there is a little bit no time probably. So I would like to skip this part and focus on the construction for this one for U1 case. The original explanation is a U2 case, but U1 case is included U2 case actually. U1 monopole is some limit of the U2 monopole. So now construction work well. Okay, so let's solve this norm equation for k equal 1. So one Dirac monopole case. This is trivial because k equals 1 by 1 matrix. So commutator automatically drop out. So the solution is just Ti equal constant. So for simplicity, we set that this is 0. So this is perfectly trivial solution. And in the second step, we solve the ordinary differential equations in the background of this norm data. This is also trivially solved. And finally, we get the following non-trivial gauge field and Higgs field. And in fact, this phi represents the position of the D3 brain. And I skipped the D brain interpretation. So the following explanation is only for the string theorist. I'm sorry. That this monopole is realized by the D1 and D3 brane system. So D1 brane ended on the D3 brane. And now G equals U1. So the number of D1 branes is 1 now. And also, this is one monopole, and the D1 brane is also 1. There is one D1 brane transversed in this figure. And phi represents the position of the D3 brane. And T represents the position of the D1 brane for the transverse direction. So this is, in some sense, consistent. And this phi have the 1 over R slope. This is realized by the D brane. So D1 brane has the tension, and the D1 brane attached the D3 brane. So D1 brane pull the D3 brane a little bit. So there is a rod shape configuration here. So this rod shape configuration just corresponds to the 1 over R. So this is consistent. And this is a non-commutative space solutions. In the non-commutative case, the coordinate always appear in pair in large T. So this large T just corresponds to the A mu tilde. So the commutator of T1 and T2 guarantee the existence of the commutator of the coordinate x1 and x2. Now, non-commutativity is introduced by x1 and x2. The commutator of the x1 and x2 equal to I theta. So norm equation have this constant theta. So this theta can be absorbed to the T3. So the solution is deformed by theta. So T3 is now have the linear function of Guzai. So in the similar way, we can construct the monopole solutions. And this is very, very rough representation. But we can find this Higgs field have the linear terms here, linear of X3 terms here. So this is consistent because from D1 brane side, in the third direction, this is a Higgs field. There is a slope in the Guzai direction, and the slope is just a minus theta. So in the figure, the red line have the slope. But on the other hand, from D3 brane, the phi have the slope. The slope is 1 over theta. So this is just this figure. So now D3 brane pulled the D3 brane. And D1 brane is a part of this D3 brane. We can interpret it. So this slope just corresponds to this X3 slope. And from D1 brane, the slope is theta. And from D3 brane, slope is 1 over theta. So this is consistent. And I forget to say, the endpoint of D1 brane has a magnetic charge on D3 brane. And the non-commutative extension just corresponds to the background magnetic field. So now we introduce the background magnetic field. Then endpoint have the magnetic charge. So this is pulled in the X3 directions. But the D3 brane have the tension. So finally balance. So this final configuration is perfectly coincide between the string picture and the field theory picture. So we can say the effect of the non-commutative parameter theta just corresponds to the presence of the background magnetic field. So the non-commutative extension has the physical meaning, the presence of the background magnetic field. Okay, so finally, I'd like to mention the magnetic field. So left side is the commutative spaces. So this is a hedgehog magnetic field. So there is a monopole at the origin. And this is a Dirac monopole. So actually, the gauge field have the singular locus, so which is called the Dirac string, which is singular for gauge field. But in the non-commutative spaces, this Dirac string becomes visible in some sense and regular, not singular. So in the non-commutative extension, this singular locus is also resolved in this sense. Okay, so finally, let's conclude. So we construct the instantons from the ADHM constructions. And we also discuss the extension of non-commutative spaces, and we see the equivalence of the non-commutative extension and the presence of the background magnetic field, and which give rise to the resolution of the singularity and new physical objects, such as U1 instantons, and so on. And this is a story of the global solutions. But the local solutions of self-Dirac equation are also very interesting and relate to the integral systems, such as KDB equation and so on. And there are recent works by ours and the Chinese member and so on. And this is actually a hot topics, I think. And I plan to hold the following workshop on unification of integral system on 27th to 29 October next month at Nagoya University and online. The speaker is the dream member, so Benu Bisedo-san and Yamazaki Masahito-san and Yoshida Kentora-san and so on. So except me. And yeah, why this is related to the self-Dirac music, this one, is the four-dimensional Bess-Witte model here. The equation of motion of this model is just the self-Dirac equation and give rise to various integral systems such as KDB and so on via the word conjecture. So today's final comment relates to this right side. On the other hand, there is a very hot study of the four-dimensional Chern-Simons theory. This gives rise to the various solvable models such as spin chains and chiral models and so on. And very recently, these two master equations can be obtained from six-dimensional Chern-Simons action, but as a double fibrillation. So under this double fibrillation, there should be the non-trivial duality between the four-dimensional Chern-Simons and the four-dimensional Bess-Witte and the reduced solvable model and the integral system. So this is very, very exciting. And so I believe this might be the new step of the study of the integral systems. And I found just today, the five-dimensional Chern-Simons action give rise to the KP equation. So KP equation is a very, very important for the Sato theory of the soliton. But so far, self-Dirac music cannot derive the KP equation. But today, they seem to successful in deriving this KP equation from five-dimensional Chern-Simons action and so on. So I believe this would be very, very exciting and very hot. So you are very welcome to join this conference. Okay, thank you very much.
Excuse me, I have a problem on microphone. Thank you very much for a nice review. Are there any questions, comments? Okay, if not, let's thank the speaker again. Thank you very much. So this is the end of the third day of the workshop. So see you tomorrow at 9:30 in China and 10:30 in Japan. Okay.
Okay, thank you very much. So I close this one. So thank you very much.
Thank you.
はい、明日もよろしくお願いいたします。